Imagine standing at the bottom of a man-made canyon. The dust is thick, the air tastes like diesel exhaust and crushed rock, and the solid ground beneath your heavy boots is vibrating. It starts as a low, rhythmic rumble, a mechanical frequency you feel deep in your chest long before you actually hear it. Then, rounding the corner of the steep haul road, it appears. But your brain struggles to process the sheer scale of what you are looking at. It is painted a bright, alien mint green. It possesses 6 wheels instead of 4, and each of those heavy rubber tires is over 10 feet tall. It blocks out the sun, casting a shadow the size of a 2-story suburban house. When fully loaded, this single machine weighed over 1,200,000 pounds. For 25 years, it held the undisputed title of the largest, highest-capacity mining truck on the face of the earth. It was a freak of engineering, an absolute, unapologetic monster born in an era when the only accepted answer to a mechanical limitation was brute force and raw American steel. But here is the most incredible part of its history. In the relentless, profit-driven, mass-producing world of heavy industry, they only ever built one. No sister ships, no fleet, just one solitary, colossal giant. This is the story of a 350-ton gamble, a machine that was half off-highway truck, half freight train. This is the legend of the Terex 3319, universally known simply as the Titan. To understand why the Titan was ever conceived, you have to understand the aggressive, unforgiving mindset of the early 1970s. In the American mining industry, the rulebook was brutally simple: move more dirt, make more money. Open-pit mines were digging deeper into the earth, the ore grades were dropping, and the global demand for copper, iron, and coal was skyrocketing. The only mathematical way to keep the ledgers in the black was absolute scale. Throughout the 1960s, haul trucks grew at a terrifying pace. They went from 50 tons to 85 tons to 100 tons. But by 1973, the industry hit a massive brick wall, and that wall was constructed entirely of rubber and steel gears. You see, you cannot just keep scaling up a standard 2-axle truck indefinitely. If you dumped 200 tons of blasted rock into a conventional dump box, the sheer physical weight would literally crush the available tire technology of the era. If the tires miraculously survived the compression, the mechanical transmissions would violently snap under the immense torque required to move the load. The pure physics of the 1970s simply said, "Stop." But General Motors did not like being told to stop. Most people know GM for building Chevrolets and Cadillacs for the highway, but back then, they owned a massive, heavy equipment division called Terex. And Terex was locked in a bitter, bloody war with legendary companies like Caterpillar, Wabco, and Unit Rig for total dominance in the world's deepest pits. Terex did not just want to beat the competition. They wanted to humiliate them. They wanted to build an undeniable flagship, a machine so outrageously massive that it would cement their legacy in the dirt forever. The engineers at Terex sat down at their drafting tables with an impossible corporate mandate: build a truck that can carry 350 tons. To put that in perspective, the biggest trucks in the world at that exact moment were struggling to carry 170 tons. Terex was proposing to more than double the industry standard overnight. It was the heavy equipment equivalent of the Apollo moon landing. The first impossible problem was the weight. When you combine 350 tons of payload with the immense weight of the truck itself, you are looking at a gross vehicle weight of over 600 tons rolling on unpaved dirt roads. The engineers looked at the standard 2-axle, 4-wheel mining truck design and immediately threw it in the trash. It would not work. The tires would pop like cheap balloons under the load. So they borrowed a heavy-duty concept from highway tractor-trailers and the rail industry. They stretched the massive steel frame and added a third axle. The Titan would have 2 steer wheels up front and 2 sets of dual-driven wheels in the back, a tandem rear axle, 8 tires in the rear, 2 in the front. It made the truck look incredibly strange. It made it look exceptionally long, almost like a massive green iron centipede, but it successfully spread that colossal million-pound weight over 10 tires instead of 6. But adding heavy axles was the easy part of the equation. How do you actually get 600 tons to move up a punishing 10% grade out of a deep mine pit? There was no truck engine on Earth that could generate that kind of power. There was no mechanical transmission tough enough to handle that twisting force without turning its own internal gears into hot metal shavings. So, Terex engineers did not look to the automotive world for a solution. They looked directly to the railroads. If you open the hood of the Terex Titan, and by hood, I mean you have to climb a 2-story flight of steel stairs to access a deck the size of a backyard patio, you will not find a conventional truck engine. You will find an electromotive division, or EMD, 16-cylinder diesel. If that designation sounds familiar to train enthusiasts, it absolutely should. It is the exact same massive engine used in heavy freight locomotives pulling miles of fully loaded rail cars across the country. It is a 2-stroke diesel power plant that displaces a mind-bending 169 liters. That is over 10,300 cubic inches. It came equipped with a massive root-style blower forcing air into the huge cylinders, generating a staggering 3,300 horsepower. Just starting this engine sounded like heavy artillery fire. It was deafeningly loud, it was dirty, and it was violently powerful. But here is where the mechanical genius of the Titan truly lies. That massive diesel engine, it was not mechanically connected to the wheels. There was no drive shaft. There was no mechanical transmission to brake. Instead, the Titan utilized a diesel-electric drive system. The EMD locomotive engine sat directly in front of a massive General Motors alternator. The only job of that roaring 16-cylinder engine was to spin that alternator to generate high-voltage electricity. That electricity was then routed through a heavy control cabinet the size of a household refrigerator and sent all the way to the back of the truck. Inside the steel hubs of the rear wheels, all 4 rear sets were individual GM electric traction motors. The Titan was not truly a mechanical truck. It was a mobile, diesel-powered electric power plant that just happened to have a massive steel dump box bolted to its back. This solved the impossible transmission problem perfectly. Electric traction motors provide maximum pulling torque at 0 revolutions per minute. When the driver put his heavy boot down on the throttle, the diesel engine would roar, the alternator would scream, and an unstoppable, invisible wave of magnetic force would instantly turn those massive tires, pushing 600 tons of steel and rock up the mountain without shifting a single gear. Getting the Titan up the mountain was an engineering triumph, but getting it safely back down the mountain was a literal matter of life and death. Imagine 600 tons rolling down a steep, dirt haul road. If you tried to use conventional mechanical friction brakes to stop that much mass, the immense friction would literally melt the heavy brake assemblies and catch the entire truck on fire in a matter of seconds. So, how do you stop a building on wheels? You use the electricity against it. The Titan relied on a heavy-duty system called dynamic retarding. It is a beautifully simple, highly effective concept. When the driver took his foot off the throttle and engaged the retarder pedal, the system effectively threw a massive electrical switch. Those 4 electric motors in the rear wheels stopped acting like motors and instantly turned into massive generators. As the sheer momentum of the falling truck forced the wheels to keep turning, those generators fought back hard, creating massive electrical resistance. This invisible magnetic drag slowed the truck down safely, smoothly, and without using a single mechanical brake pad. But that heavy resistance created a terrifying amount of electrical energy. Where does that lethal energy go? It went to a massive bank of heavy resistor grids mounted directly behind the driver's cab. These grids were essentially giant industrial toaster coils. The raw electricity was pumped straight into them, converting the deadly kinetic energy of the falling truck into pure, intense heat. Giant cooling fans would then blast that heat straight up into the atmosphere. When the Titan was coming down a mountain fully loaded under heavy retarding, you could actually see the thick heat waves violently distorting the air above the cab. It was bleeding off thousands of horsepower of pure thermal energy just to stay in control of the descent. By 1974, the Titan was finally ready. But building it in a sterile factory was one thing. Getting it to a working mine was a logistical nightmare. You could not just drive it down the interstate highway. The Titan was 66 feet long and 25 feet wide. It was so massive that to move it from the factory floor, it had to be completely disassembled, loaded onto 8 heavy flatbed railroad cars, and shipped across the country in pieces. Its first real trial by fire was at the Kaiser Steel Eagle Mountain iron mine in the scorching heat of California. A dedicated crew of heavy welders and mechanics spent weeks just putting the monster back together on site. When it finally rolled into the dirt, it was an absolute spectacle. It dwarfed every other piece of equipment on the property. When the massive electric shovel operators loaded it, it took bucket after bucket after bucket to finally fill the cavernous bed. The productivity numbers were staggering. It could do the grueling work of 3 normal haul trucks combined. But as the long months wore on, the initial romance faded, and the brutal, unforgiving reality of open-pit mining took over. The Titan was an undeniable engineering marvel, but it was an absolute operational headache. First, there was the turning radius. Most standard mining trucks have 2 axles and can turn relatively tightly on narrow benches. The Titan, with its massive long wheelbase and tandem rear axles, maneuvered like a heavy battleship. Haul roads had to be widened specifically to accommodate it. Shovel operators had to completely change how they positioned their loads because the Titan needed so much extra room to spot underneath the dipper. Then there were the tires. Remember why the engineers added the 3rd axle? To save the tires from being crushed? Well, it did not quite work out that way in the dirt. When the Titan navigated a sharp, heavy turn, those tandem rear axles violently fought against each other. The tires would scrub, drag, and tear against the razor-sharp rocks of the mine floor. It was eating 10-foot-tall tires at a rate that made the mine accountants physically ill. And finally, the maintenance. Keeping a one-off, highly experimental prototype running in the harshest environment on Earth is a mechanic's worst nightmare. There were no spare parts sitting on a shelf in a warehouse. If a custom component broke, the massive truck sat idle while a replacement was fabricated from scratch. And in the high-stakes mining business, an idle truck is bleeding serious money. In 1978, the Eagle Mountain mine began winding down its operations. The mighty Titan was suddenly out of a job. It was purchased by a new company and shipped once again, completely in pieces to the frozen, unforgiving environment of the Sparwood coal mine in British Columbia, Canada. They repainted it from its original Terex lime green to the blue and yellow colors of the new operation, and here In the freezing Canadian Rockies, the Titan found its final, grueling battleground. For over a decade, it hauled heavy coal. It survived freezing temperatures that made its thick steel brittle. It survived the choking dust, the deep mud, and the endless, punishing grind of 24-hour operation. Despite its obvious flaws, despite the brutal tire wear and the constant maintenance headaches, the men who drove it and the mechanics who wrenched on it developed a deep, begrudging respect for the sheer, stubborn durability of the heavy iron machine. But time eventually catches up with everything in the dirt. By the late 1980s, the rest of the industry had caught up. Tire technology had drastically improved. Companies like Caterpillar and Komatsu were figuring out how to build reliable 240-ton and 300-ton trucks on just two standard axles. The cumbersome, heavy, three-axle design of the Titan was suddenly a relic of the past. In 1991, after moving millions of tons of heavy earth, the locomotive engine of the Terex Titan was shut down for the final time. Normally, when a machine this incredibly big dies, it is cut up with heavy acetylene torches and sold for scrap metal. But the Titan was different. You do not scrap a legend. The mining community of Sparwood recognized exactly what they had. They rallied together, raised the funds, and saved the beast from the scrapyard torches. They meticulously restored it, painted it back to its original factory, Terex green, and parked it permanently right off the main highway. Today, if you drive through the Canadian Rockies, you can pull your truck over and stand right next to it. You can touch the cold iron. You can look up at the massive front grille that blocks out the sun, and you can truly feel the sheer, terrifying scale of what men dared to build 50 years ago. Was the Terex Titan a failure? Some spreadsheet accountants might say yes. It never went into mass production. It was too complex, too thirsty, and too hard on its own running gear. But to look at it as a failure is to completely misunderstand what it actually was. The Titan was a massive, heavy-duty experiment pushed to the absolute physical limit. It proved beyond a doubt that diesel-electric drive could handle unimaginable payloads. It forced tire manufacturers to innovate to survive. It forced the entire heavy industry to think bigger. It was a machine born of pure American industrial audacity, a magnificent 305-ton mistake that ruled the earth for a quarter of a century. It stands today to remind us of a time when the answer to a tough problem was not a simple software update. It was a massive 16-cylinder train engine and 1 million pounds of cold, hard iron.